Fortunately, I didn't upload the blank slides ahead of this, so they're not there. But it builds very similar stuff off of what we did last time. Okay, so we've talked pretty extensively now about sine waves, and I'm going to just kind of blow through this. I mean, we've said and have kind of beat to death this idea that sine waves occur frequently in all of our ECE problems, and we've given a number of examples as it relates to basically audio signals, power waveforms, radio waveforms, those kinds of things. And even if they're not sine waves, you know, we basically say that as long as they're periodic, that they can be represented as the sum of sine waves, and we can still use this approach we've been talking about. So basically we've said, okay, two types of circuits that we'll think about. So static circuits that only have resistors, and dynamic circuits that have R's, L's, and C's. And as it relates to, you know, really these two situations, we said if we have sinusoidal inputs in these circuits, when I say inputs, I mean sinusoidal voltage sources or current sources that we're using. And if we care only about steady state, then the analysis becomes pretty straightforward. So we looked at a static circuit first, and we said, okay, well, what happens if I put a sinusoidal source into a voltage divider like this? And basically, you know, we talked about this. So you guys, again, I'm going to ask the same question I've asked a couple of times now, right? If I look at this here, if I have a sinusoidal input like this, V out being the voltage across that resistor, is that voltage across the resistor? Somebody describe to me what that voltage is going to look like. If I have V in is 10 sine 2 pi 100t, what will its frequency be? And will it be shifted left or right? What will be the frequency of V out?
Wouldn't the frequency be the same?
Yeah, frequency would be the same. And would it be shifted?
No.
No, right? Because when we're talking about resistive circuits, everything lines up, right? So basically what we said is I basically can just do my analysis looking at just the amplitudes. Basically here I've got the input voltage that this is that 10, basically the 10 sine 2 pi 100t. Okay. That's the 10 sine 2 pi 100t. And, you know, I have the output voltage there in red and the current there in the yellow. All of them have a sine 2 pi 100t, but I don't even need to use that sine 2 pi 100t. I just need to track what's going on with the amplitudes. Okay. All right. Now, when I look at a dynamic circuit, similar approach from what I did in this case, I've got a circuit that has a resistor and a capacitor in series. And we said, not knowing anything else, we would have to write a differential equation for that circuit. The solution to that differential equation would have a transient response and a steady state response. We basically said, we looked at the frequency. So my input source was cosine 2 pi ft, and I changed the frequency f to be a couple of different values. So 0.1 hertz, 10 hertz, 1,000 hertz. Basically what we saw with that is the amplitude decreased as the frequency went up, and the waveform was shifted, all right? And in fact, if blue is the input here and red is the voltage across the capacitor, which of those two waveforms is leading? Which one would be the leading waveform? Blue, right? Whichever one peaks at an earlier time is the one that is said to be leading, okay? All right, so basically what we summarize with this is if we have a circuit with only resistors, the frequency stays the same, the phase changes the same, and the amplitude can change, okay? Capacitors and inductors in our circuit, all the frequencies of all the voltages and currents are always the same, but there might be phase shifts. In other words, the waveform might be shifted left or right, and the amplitude might change a little bit, meaning that the sine or cosine could be scaled bigger or smaller. But basically what this meant is that when we do our analysis, what we need to do is we need to make an understanding of what's happening to the amplitude, right? We only need to understand what's happening to the amplitude. Sorry. Don't want me to work on my screen today. The amplitude, all right. and the phase. You know, I'm gonna hang on for a second. I'm gonna go out of full screen there for a second. So once it'll allow me to work on amplitude. Hang on, guys. Sorry. I'm sitting in a weird spot. I think it's got me messed up here. All right. Amplitude and phase are the two things that can change. Okay. Now, all right, I'm going to give up on trying to write that. Basically, what we said is if only the amplitude and the phase can change, then instead of using the whole time domain waveform, what we do is we shift over to making use of what we call the phasor. And we transferred from the time domain to the phasor domain. And we wrote this phasor as a complex vector that has a magnitude and an angle. All right, so for the waveforms that I'm showing right here, right, this is from that circuit at 10 hertz. What I see is that V in has an amplitude of 1, and because it was cosine, it has an angle of 0. And V out was basically, it had an amplitude of 0.704, right? And then it had an angle of negative 47 degrees, okay? All right, so we talk about these things in basically as complex numbers, and we'll look at some more examples of that. Now, basically, this allowed us to kind of generalize our results and to talk basically in the context of what we defined as impedance, okay? So we said that if I have a resistor, it has a particular impedance. A capacitor has a particular impedance. An inductor has a particular impedance. And you know what we know, or what we knew basically, is if I had a capacitor, I know that, man, it doesn't really want me to write on the screen here today. The capacitor voltage, wow. Yeah. The capacitor voltage sorry guys. Capacitor voltage, or capacitor current really, right? I sub C and I sub C equals C dVc dt. And we know that for the inductor, V sub L equals L di L by dt. What we said is that when we have sinusoidal stuff, we can basically relate their phasors using this relationship here. And we can relate the phasors using this relationship here for the inductor. And we have this kind of generalized statement of Ohm's law that we use, where V equals I times Z. Okay. Now, that information tells us some important stuff, right? So we talked the other day. So if I say V equals IZ, let's go over here to the inductor, right? So if I go over here to the inductor and I have basically for this guy in steady state, I basically have that V sub L equals Z sub L times I sub L. And Z sub L is J omega L times I sub L. What do we know about the phase relationship here? We said that this is actually two equations, right? So there's an equation for the magnitude here, and there's an equation for the angle. Okay. So what's the equation here for the magnitude? What do we know about the magnitude relationship? How does the magnitude of V relate to I? How do we relate their magnitude? Somebody knows.
Did you say dear Z?
How does the magnitude relate? How does the magnitude of V relate to the magnitude of I? For this equation right here, right? How do they relate?
They're directly proportional.
They're what?
They're directly proportional.
They're proportional, right? Basically, I mean, give me an equation for it. It's the magnitude of V, right? So you'd say the magnitude of V. Sorry here. It's really not like in my is equal to the magnitude of I, and they're proportional, times omega L, right? And this is stuff you guys have already studied in 2254, right? If I have two complex numbers multiplying each other, I sub L and V sub L are complex numbers. J omega L is a complex number, right? So the way that I look at this is I say, here, J omega L is a complex number. I sub L is a complex number. So if I have the product of complex numbers, their magnitude is the magnitude of the product, okay? And this Z sub L here, just remind ourselves, Z sub L is a complex number. Yikes. Z sub L is a complex number whose angle, and let's just, if I have this value right here, Z sub L is J omega L. What is its magnitude and what is its angle?
The angle of I plus 90.
What's the magnitude of Z sub L? In other words, this complex number right here, what is its magnitude? Whoever just said that, you guys, you were talking about the V sub L, which you were correct about. But if I just look at the Z, the impedance, the Z equals J omega L, what's the angle of that complex number?
90 degrees.
90 degrees, right? So yeah, exactly what you just said there. The angle of V sub L would be equal to the sum of those two angles. So basically 90 degrees is the angle of J omega L, and I add that to the angle of I sub L, okay? And I would do a similar thing for the capacitor. The difference with the capacitor is V would be equal, the angle of V would be equal to negative 90 plus the angle of I, okay? So basically for these two things here, basically what I can say is for the capacitor, I can write this essentially as kind of two expressions, I guess, if you will. And I can think of each of these. This guy has a magnitude, which is 1 over omega c, and he has an angle, which is negative 90 degrees. This guy, on the other hand, has a magnitude of omega L, and he has an angle of 90, okay? What about for the resistor? What's the angle for the resistor?
Zero.
Yeah, that's going to be 0, right? The angle of Z sub R is equal to 0. The magnitude of it is just equal to R. So technically, we've been using this all along, even in circuits 1, right? So the magnitude is R, the angle is 0 degrees. So, question would be is, what does this all mean and how do we utilize it, right? And so we're going to look at some examples here today to try to get us more of a sense of how to use this thing. So let's say I've got this circuit here where I've got an inductor, all right, a capacitor and a resistor that are all in parallel with each other, right? So I'm going to say this is, oh boy. Sorry, this isn't working too well here today. I'm not sure what's going on, why it's fighting me so much. It's the resistor, and it's really fighting me. Let me reorient myself here for a second. I have R, C, and L. And I'll call this guy here I of T. Okay. And so the circuit we said exists in what we call the time domain, but we map it. So this is what we call the time domain. Time domain. And then it also includes what we refer to as the phasor domain. This is what we map it to, the phasor domain. In the phasor domain, we represent everything with the impedances, okay? So over here, I would write, this is I. This would be, so if I refer to the currents, you know, these would be time domain values. So IL of T, IL of R, or sorry, IR of T, and IC of T. These guys would be instead phasors. In other words, they would be complex numbers. And we said the other day, right, same thing, you know, sort of applies in these, we talked about the other day. The time domain is what you build in the lab. It's what you see in the real world. You take a source, you hook a source up to the circuit, and you make measurements, and you see waveforms. In the phasor domain, you're looking at complex numbers, okay? So I'm gonna make a couple of definitions here. I'm gonna say that I want I of T, the source here, I of T to be equal to I cosine, say 2 pi 1000 T plus 30 degrees. All right. And let's say that I is going to be equal to 4 amps, like that. So I want to basically map this circuit over into the phasor domain. And I'm going to give values here for L, R, and C. So let's say L is 1 millihenry. Let's say R is 100 kilo ohms. And let's say C is 1 microfarad. All right. So the first thing I want to do is I gotta map this guy over to the phasor domain. So I gotta first figure out what I of T becomes as a phasor. So if I of T is what I've defined here, I cosine 2 pi 1000 T plus 30 degrees, what is my phasor I? What would that be for this particular circuit? So what's the phasor that goes with this?
4 angle 30.
4 angle 30. Now, you guys should know from 2254, how do I get this in rectangular form? Say I wanted it in rectangular form. How would I do that? Four angle 30.
You put it in terms of cosine sine.
Yeah, so what I typically do is I could say 4 cosine 30 degrees plus J times 4 sine 30 degrees. Now, one thing I'm going to do today, which I'm pretty sure that Yahoo has gone over with you guys, is I can write this in Euler's form like that. Have you guys seen that last form? 4e to the j 30 degrees with Yahoo yet? You guys just give me a yes or no whether you've seen that with Yahoo.
Yeah.
Okay. All right, good. Just want to make sure. It's pretty sure, but all right. So those are the 3 ways that I can do it. And I'm doing that for a reason, because I want to enter this guy and use it to do some computations a little bit. All right, now what I got to do though is let's say that I want to figure out a couple of different things. Let's say first thing I want to figure out is the voltage across the capacitor. Okay. So let's say I wanted to figure out the voltage across the capacitor. So if you wanted to figure out the voltage across the capacitor, how would you do that? What would be the approach to figuring this out?
Current through the capacitor times the impedance of the capacitor.
Yeah, I could find the current through it times the impedance. That's what I do in the phasor domain. If I wanted to get the answer in the time domain, I would have had to write the differential equation, right? And you guys probably would have done nodal analysis to do that. What I'm going to do here, though, I'm going to do it in the phasor domain. And I'm going to say, I can solve for the phasor V sub C, which I'm going to define that way, right? Because basically with impedances, I'm using Ohm's law again. And so I got to make sure I use the passive sign convention and everything. All right. So if I have this set up here, I don't know what I sub C is right off the bat. So if I gave you basically 3 impedances in parallel like that, one thing we talked about the other day is when we go to impedance, I could derive this, but I want to get into examples. Basically, impedances in series add just like resistors in series. Impedances in parallel combine just like impedances, or just like resistances in parallel add. So if I said to you, all right, I don't want to use nodal analysis, but what I want to do is I want to combine those impedances. You would say that those impedances are in parallel, right? So if I'm looking at this particular circuit, what I have here is C sub L, C sub C, and Z sub R, right? They're all in parallel with each other. So isn't it true that for this circuit, so again, I'll redraw it here. If I have the phasor I won't call it I sub S, I'll call it I. And here's Z sub L. Here's Z sub C. And here's, I could say Z sub R, but I usually just say R because the R and the impedance Z sub R are the same, right? And here is V sub C. I want to solve for V sub C. I can say that V sub C is equal to what times what? Well, it's I times the parallel impedance, right? So I can say this is the way I write impedances in parallel. I say Z sub L in parallel with Z sub C in parallel with R. Okay. So this guy right here is what I would call the equivalent impedance, ZEQ. Okay. So ZEQ is ZL in parallel with ZC in parallel with R. So without substituting in these expressions ZL, ZC, ZR, if I just thought of those as 3 resistors, what would be the formula in terms of ZL, ZC, and R for the equivalent impedance? If they combine like
1 over each of them.
yeah, 1 over
Sorry.
1. Yeah, no, you got 1 over each of them, right? So 1 over Z sub L plus 1 over Z sub C plus 1 over R, like that. All right. And that's, I could simplify that in some form, but it's ugly to begin with, right? And it's even uglier to me. I could then put in, the values for Z sub L, but I need to get some numbers for ZL. I didn't give you numbers for those, right? What I gave you numbers for was L, R, and C. So how do I approach this guy now? What do I have to do next? What have I not done? I got to calculate ZL, right? I got to calculate Z sub C, and I got to calculate R. Well, R I already know is 100 kilo. What is Z sub L? How do I calculate that?
J omega L.
J omega L. So that, in this case, J omega L would be J times, what do we put in for omega here? I can tell it's 2 pi 1000 T plus 30 degrees. So what do I put in for omega?
would be 2 pi 1000.
2 pi 1000, because basically, yeah, the source that I'm putting into this circuit, this guy right here, has a frequency of 2 pi 1000, radian frequency. So what I do is I say it's J times 2 pi 1000 times 1 millihenry. So that times 10 to the negative 3. So if you're paying along careful attention, that's going to basically be 2 pi, right? If I run those numbers. What about Z sub C? What do I do for that? What's the formula for the capacitor impedance?
One over JWC.
Yeah, 1 over J omega C. Right? Which is, if I go through, in this case, it's the same approach, right? 1 over J times 2 pi 1000. I put the same frequency omega in there. And my value was 10 to the minus 6. Okay. I can run through the numbers for that. I basically plug all that stuff into here, and I got to be real careful about this whole thing because I got J's and 1 over J's and all that kind of stuff. I usually don't do much simplification beyond any of this stuff. All right. What I want to do here real quick is I want to say to myself, all right, what is this? How would I do the math at this point? And how would I kind of put this into MATLAB? So, because, you know, I'm going to ask you guys to solve these things in MATLAB. And this is where I think MATLAB is a much more powerful and capable tool than what you're used to dealing with on your calculator. So let me try to put these two things sort of side by side here. So I'm going to put this guy and this guy side by side. All right. So what I've done here is I have defined for myself the phasor, all right, for the current. I equals 4 times, and so notice what I did here. Let's compare this with this expression here. All right, so here was the expression for the phasor, right? 4e to the j 30 degrees, so 4 angle 30 degrees. The way I enter that into MATLAB is I use what you see on line 3 here on the left. Now, so I did 4 times exponential, so exp is the formula that we use. What the heck's going on here? I have j times 30 times pi over 180. What the heck is that?
Converting it to degrees.
Converting it to degrees. All right. All of MATLAB's internal functions are based in degrees. Or sorry, based in radians. All of MATLAB's internal functions are based in radians. There is no xd function or anything like that. Exponential is essentially a trig function that's defined in terms of radians. Okay, so I could do it this way. If you're not comfortable with that, the other thing that you could have done, which is entirely the same thing, is you could have used the rectangular form, right? 4 times cosine 30 degrees plus j times 4 sine 30 degrees. Now again, you probably would have to do that. You'd have to convert those angles over to radians to be able to use cosine and sine directly, right? Otherwise, you have to convert that angle to radians. Okay. All right. Now, notice what I did here is I defined also my my L. So on the left side here, I made my L value is 1 millihenry, my C value is 1 microfarad, my R value is 100 kiloohms. And then I wrote out for myself Z sub L and Z sub C. And then what did I do here? Well, I defined Z parallel, right? So Z parallel, which we wrote here, all right, this was our Z. I guess I called it ZEQ in my slide, but I called it Z parallel here. I don't know, I'll call it, just to be consistent, I guess I'll call it ZEQ, okay? And notice what I did, I just did 1 over those things, and then they're all combined like that, okay? So if I wanted to solve for V sub C, we basically said how to do that. Oops. Right, V sub C was basically looking here. Not reacting to me here. All right, V sub C. No. V sub C was, or if I expand this out, V sub C is I times ZEQ, right? So what I want to do is in my MATLAB, if I want to figure out what V sub C is, I would just do I times ZEQ. Okay. Now you could, that's a complex number at this point, right? So if I solve this, anybody know what the format's going to look like? If I try to run this in MATLAB, what will that look like? Has anybody run something like that for, say, problem 4 on the homework? What will that look like? Somebody's run that. What form is it in? Rectangular or polar? Let me phrase it that way. Now it's going to be in, may not have looked at the answer, right? But I see it here. Okay, so that's clearly a rectangular form, the way that it output that. MATLAB doesn't write the J, it writes I instead. So I see that I have this particular guy right here. Now, if I wanted to figure out the magnitude and the angle of this particular vector, maybe Yahoo has shown you how to do this, but way I do it is so if I just look at the result again, all right, so you've got this complex number. You guys tell me here. Here's the complex number, -13 plus 22j. If I wanted to figure out the angle of that, how would I do it?
That'd be imaginary over real plus or minus pi.
You do the arctan of that, yeah, and how would I get the magnitude of it?
It's the square root of both, right?
It's the
After you square them both.
yeah, square root of real part squared plus the imaginary part squared, right? Now, turns out MATLAB has some nice built-in functions that I'm going to use here. What I do is it's got a function called ABS or ABS, which is going to tell me the magnitude. And again, that's just going to basically be the square root of the real part squared plus the imaginary part squared. It also has a function called angle. And angle's nice because angle takes into account for me which quadrant it's in, so I don't have to think too hard about doing the shift. But its answer is going to be in radians, so I'm going to multiply it by 180 over pi to convert it to degrees. Now, I'm going to ask you, before I run this, I want to ask you guys intuitively, if I'm looking at this guy, -13 plus 22j, what quadrant is this guy in?
Two?
Quadrant 2. So the angle should be between what and what?
90 and, or no, wait, yeah, 90, 180.
90 and 180. Okay. And so let's see if it does that. I'm going to run this. So in MATLAB, what I always do is I just highlight that. I right click and I do evaluate selection. And then I go to my command window. So it told me that the magnitude was 26.1657. And the angle was basically 120 degrees. So that makes sense. We said it's in the second quadrant. Okay. So basically go back to my, oops. All right, we'll go back to here. So basically what I ended up with is I said V sub C is equal to I times ZEQ. And we just said that was 26 something. I'm going to just round it to 26. And I say the angle associated with that guy was 120 degrees. Okay. All right. So that's the phasor for the voltage across this thing. So what I solved for here was basically this phasor. Now what I want to do is I want to ask myself, okay, let's take a look at a couple of different things. I want to look at basically, all right, my I and my V sub C. So I was over here. This guy is 4 angle 30 degrees. And V sub C would be basically over here, and he'd be longer because his magnitude is 26. So again, looking at these two things, which one of those vectors is the leading vector? Which one of those vectors leads?
BC.
Yeah, BC leads, right? We said the one that's more counterclockwise is the one that is leading. All right, so I want to talk about what this guy is in the time domain. Okay, so if I told you I have V sub C is this phasor, I want you guys to tell me, what is V sub C of T going to look like? What would be the time domain function? It's a cosine, right? What's its amplitude, frequency, and phase? How do I basically reverse convert this thing? So I have 26 angle 120. I want to convert that from the phasor domain back to the time domain. So what does that mean? That means I want to get a cosine function. So what's the amplitude of the cosine?
26.
26. And what's the frequency? We got to go back to whatever the frequency of the source was, right? The frequency of the source that I had was 2 pi 1000. So all my impedances and everything is in terms of this 2 pi 1000, which is the omega of the source. So I say this is cosine 2 pi 1000 T plus 120 degrees, like that. All right. And so now what I can do is I can graph that, and I can graph I sub C to see what the two of them look like. All right. It's a pretty straightforward approach. If I had done this, with differential equations, I would have done nodal analysis, and it would have been, kind of an ugly second order differential equation that I would have had to create. What I did here basically is I move everything over into the phasor domain, use complex numbers, and it's basically an algebra problem instead of a calculus problem. All right, and it's a much more straightforward problem for us to be able to solve. Right now, let's say, for sake of argument, that I had said, all right, I wanted you to tell me. So I have L, I have C, and I have R. Let's say I wanted you to tell me I sub R. How would I figure out the phasor? Let's do it that way in the phasor domain. How would I figure out the phasor I sub R? What would be the approach to doing that? This is a current divider, right? How do I deal with a current divider like this? What's my general form for the current divider? So we're going to start reviewing a lot of these formulas from 2111. But if I had this set up, how would you do this if I had three resistances in parallel? How do I get that formula for what that current's going to be? Anybody know?
Would you do the current times the capacitor impedance and the inductor impedance added together divided by the total impedance?
So you're trying to pattern match, right? So, but it basically, which is a reasonable approach, but I think of it like this, right? We know what the voltage is here. The voltage was I times what we just said was ZEQ, right? Where ZEQ was the parallel combination of 1 over ZC plus 1 over ZL plus 1 over R, like that. That tells me right there, that's the voltage. This is the voltage across here. So how do if I know the voltage across the resistor, how do I get to the current? What do I have to multiply that by?
1 over the impedance of the resistor.
Yeah, so and it's just 1 over R, right? And yeah, there's there's a nice little compact formula if I have 2 things in parallel to figure out what the current is. Once I get to 3, the formula is not particularly compact. So I just look at it as, well, it's the voltage, which is basically the whatever the known current is going into the combination times the parallel impedance. That's the way I get the voltage. I divide that by the resistance to figure out what the current is. I'm going to get some phasor for this. That's going to have some magnitude and some angle, and then I'm going to convert that back to the time domain. All right, so we basically have this sort of multi-step process that we kind of keep walking ourselves through. All right. Now we're going to look at more of this Friday, and basically, really over the course of the next 2 weeks, we're going to keep repeating. I say the next 2 weeks, basically Friday, and then next week and the week after, we're basically going to be just kind of repeating all of these problems. And what are we going to be doing? We're going to be doing mesh and nodal, and we're going to be doing current dividers and voltage dividers and all that stuff. Basically repeating 2111 with these phasors. So you guys are going to get comfortable, hopefully, with how we deal with complex numbers, because the complex numbers let us be able to deal with circuits and in steady state in a much simpler way than if I had to deal with differential equations. And that's kind of the key point to all of it. All right, so I'm going to stop there. I got a couple minutes left.